Okay, hello. Um, we are in lecture 6, or yes, I think. So last week we talked about generational collection and the train algorithm, and this week we want to to start talking about concurrent garbage collection. There will be several lectures on this topic. And we'll start. So let's say what kind of platform we have in mind. So we're talking about a multi-core where we have several cores, like several CPUs, you can think of it. Each one has a cache, which will later, maybe we will talk about it, but we assume a shared memory where the heap is, and there's like a bus where everybody can access the same memory. And we'll have to coordinate the actions so that everything will work well. So this is the platform. There could be, more complicated things. There could be maybe several cores on the same processor, and then that one will have a cache, but we don't mind all of that. You can think of this as the model of the platform. And in terms of terminology, what we're saying, concurrent, parallel garbage collection. So think of this as time, and each of the line is like a core. And so what you see here in what is called Stop the World collection is you have four cores, and let the orange lines be the program execution, and the blue or purple line be the collector execution. So what happens here is the program runs on four cores. At some point it is stopped, and then the collector runs on a single core until it finishes, and then the program continues on the four cores to run in parallel. So this is a waste of three cores while this is happening, and so you will not find this today anymore. This was once popular. This is parallel, where you take this action and make it parallel, run the collector in parallel, and then you do use all the cores, so you don't waste CPU time. And this is also called parallel stop the world. It used to be called, we'll sometimes say parallel, and sometimes you'll hear uh, people say stop the world for that, because this does not exist anymore in today's machines. So stop the world is actually usually means parallel stop the world, but it could mean, sequential stop the world. In contrast to this, there is concurrent. Now, this is not an English differentiation between parallel and concurrent. This is the jargon of this specific community, where concurrent means that the collector runs concurrently with the program, and parallel means that the collector runs in parallel to itself. So this is just the garbage collection jargon. It's not like a definition of the English words. It's just how it is used for garbage collection. Concurrent garbage collection would mean that the collector runs concurrently with the program. Parallel garbage collection means the collector runs in parallel to itself. And why is the rest of CPUs? What? Here, why is this? Okay. So what you see here is that in the beginning of the collection, and we'll see why, there is a time where all the CPUs, the program has to coordinate the beginning of the CPU, and it will help the concurrent garbage collection. We will see that without help, concurrent garbage collection cannot succeed. So this is a good question. And there is another thing called on the fly, where you don't need to stop all the program threads together. You can stop them one by one, each when it is convenient to it. And what we usually require from a stopping is that it will not be in the middle of changing a pointer. You'll see this later, but there will be requirements on when threads can stop. And so if you want to stop all of them, you have to wait until all of them are in the right place to be stopped, and that will take some time. And so this is going to be longer than the stops that you just need one thread to do it when it's convenient to him. And so this is called on the fly. So the proportions are not right. First of all, if you go from sequential to parallel, you win a lot more than what it looks like here. Normally, maybe this will be 3 times shorter than this because you have 4 processors here. This the time that you spend on collection is not that large compared to the time you spend on the program and so forth. So this is not meant to give you proportions. It's just to show you qualitatively what's happening here. So between these, so you can ignore this. This will not happen. But between these, maybe some informally like thumb rules to understand what it means in terms of the pause times that you see here. You can think of it, and it's not, it's like it depends on the machine, it depends on the heap, it depends on the collector, it depends on a lot. And this is definitely not correct numbers. But just to give you the idea of what's happening here, you can think of this as taking 100 milliseconds, this maybe 10 milliseconds, and this 1 millisecond. So you can see the benefit of moving from here to here. And if I only said this, then you would think that this is the only thing we would want to use because it's the best. But there is a throughput loss. So if you do this, you have to cooperate with the collector in order to allow it to run concurrently. And if you cooperate, you run not as fast. So in terms of how much you make during, how much progress you make while you're running, here you'll make more progress because there's no need to cooperate. And here you'll make less progress. And again, as a thumb rule, think of this as a 10% throughput loss between this and this. So this is, and sometimes when you run Java, the standard Java by Oracle, you will have the ability to choose which collector you want. So if, for example, you're running against a user and you don't really care if you work, your throughput is 10% smaller, but you do want the pauses that the user feel to be shorter. You don't want pauses. You don't want the user to feel interrupted. And so you'll prefer these concurrent collectors. If you are a bank that runs lots of transactions during the night on the database, then you don't care if there are pauses. You just want things to move fast and finish by the end of the night. So you may prefer this or that if you want it to run fast or you want to see no pause. And you can choose. When you run Java, you can choose which collector will run. It remains to ask why not always use this? Why do we have this at all? And the reason here is very practical. This is a lot more complicated than this. So designing this is, we like it in academia, that it's complicated and you need to do things wisely and be careful. But in practice, when you do this in the industry, it is problematic. So maybe the garbage collector is designed by some smart people like you who finished the best university, but maybe after it's all debugged and so forth, it goes to some different team from maybe a different country or at a different level of expertise to maintain it. So the designers do not want to go on all their lives maintaining what they designed years ago. So it goes to maintenance, and then people who are not very good, very experts, cannot work with these kinds of collectors. They cannot understand it, they cannot modify it when the language changes, and they cannot maintain it. So in practice, in industry, this is very problematic. So it was tried a few times, and and many times it just didn't work to maintain it. And there are quite complicated collectors now in Oracle. We'll talk about it in the end. But through the years, many times complicated collectors did not survive. So this is the reason why many times we prefer concurrent over on the fly. Okay, so this is what we're going to do. We're going to start with concurrent. So this is the first work from '76, and it was like so you see here Dijkstra and Lamport are two Turing Awards winners. I don't know if you know, Turing Award is like the Nobel Prize in computer science. And Dijkstra won it in '72 and Lamport a couple of years ago, I don't remember. But these are very good, serious authors that did the first concurrent garbage collector. And I will show you at the end of this presentation what they said about it. But they found it surprisingly hard. So they started with it as saying, this is a great way to try parallelism, like an exercise in cooperation. Let's try it and do it and see what happens. Dijkstra started with a student, and they say that many times they had a solution that seemed to them to be correct, and it took some times, maybe sometimes weeks, until they found there is a bug in the design and they had to change it, and eventually they managed to prove it. This will be our simplest collector, but it's not. I mean, we see the result at the end. We do not go through all the attempts they made, so it looks simpler, and we will prove it. Mostly prove it in class. We will not do it with the more complicated algorithms. Okay. Dijkstra, maybe you've seen him in algorithms, right? He has a very famous algorithm for shortest path. And he was in general he did lots of very interesting algorithms. He had a huge number of papers. So he started in, he was born, he's a Dutch, he was born in Netherlands, and he studied there for his first degrees, and then he went to, he also worked as a professor in Netherlands, and then he went to the US. He worked in Austin, in University of Texas at Austin, where he was a professor until he retired, and then he returned to Netherlands. So we talked about the three-color abstraction, which was invented by him. This was done in '76. So I should say that in '76 there were basically no parallel computers. There were, but they were very rare, and all this theory behind parallelism was very in the beginning, and it was done in universities. Not much. Basically, there was almost no software that supported parallelism, and so this was really in the beginning. And so this was one of the first major algorithms in this domain. So we mark things by colors. So black, as we said, we did this in Baker's algorithm for copying. We said black is an object that we have already seen in our traversal, and we've also noticed its children. So in this case, we have like black objects that we have marked, and we have put maybe the children in a mark stack, or we've seen them. We'll not miss them in this collection. Gray are objects that we've seen, but we did not traverse their children. So we still have to work on them. And white are objects that we have not yet seen. So in this traversal. So this is what we're going to use. Here is an example of a graph. There is a wave of gray objects that we need to still traverse. Behind them, there are the black objects that we're done traversing. We're not going to look at anymore. We assume that we've seen their children and we don't need to look at them again. And white objects are in front of the wave. We haven't seen them yet, and we need to traverse them in order to mark them and not reclaim them later. Okay, so Dijkstra et al., these five authors, they said we want to not speak about all the practical issues that are less interesting for this exercise, and we want to abstract it all in a graph. So the way we'll do it, first let's talk about fixed size objects. All the objects are nodes in a graph, and they have 2 pointers. That's all. No integers, nothing else, just 2 pointers. And I should say that most of the problems that may occur are still happening in this very abstract graph. Maybe there will be differences in the efficiency when you work with the graph and when you work with the real system, but in general, the problems are still happening in this abstract graph. So we'll do everything in an abstract graph, and it will represent all the problems that may happen in the real world. So we have fixed size objects with 2 pointers in each. And what can happen is that we can allocate or free a node. We can add, delete, or redirect an edge that is going out of some node. And so we're going to make simplifying assumptions. First, there is a free list that holds all the objects that are ready to be allocated. This is standard. And also, instead of having a null pointer, we're going to we'll have a special node called nil, and all the null pointers we just point to this special node called nil. So now there are no null pointers. There's just pointers. And so I don't need to allocate or free anymore because I just move stuff from the free list to the regular graph. I disconnect them from the free list and connect them to the objects that I'm using. And in order to free, I take them from the graph and add them to the free list. So allocation and free is just redirecting an edge. Okay. And now let's talk about what's reachable nodes, which we have to find. So several nodes are defined as roots. Okay, so this is not exactly as we're thinking about it. So normally, when we talk about roots, we have roots, right? And they are pointing at some, nodes that we say are directly reachable from the roots. What Dijkstra says, let's say there are fixed nodes. They are the roots. Forget about all of this stack, global variable, stuff like that. There's just specific nodes that I call roots, and I want to see what's reachable from them. That's my goal. So we have several nodes that are defined as roots, and other nodes are either reachable or not reachable from the roots. Okay? And what we know is the program can only redirect an edge between reachable nodes. So the program has no access to nodes that are not reachable. This is a given. And now redirecting an edge can only happen between one reachable node to another reachable node. This is the only thing that the program can do. The garbage collection does not redirect edges except for putting stuff maybe during sweep. It might add stuff to the free list, but in the graph of the objects, okay, we'll also solve this soon. So let's do the final abstraction. We'll have a special root for the free list, and nil will be a root. So all the nodes in the free list are also reachable. So if I allocate an object, I take it from the free list and put it in the graph, I also only redirect edges that are reachable from nodes that are reachable, because the free list is reachable and the graph where I put it is reachable. And when I put it back, it's also like that. I put it in the free list where it's reachable. So now the program, the only thing that can be done, there is no allocation because it's just moving from and to this free list, which is reachable. And there is no null, so I cannot create an edge or delete an edge. I just redirect an edge. That's all that can be done on this graph. So The program can only redirect an outgoing edge of one reachable node to point to another reachable node. That's the only action that the program can do after all this abstraction. And now we have to do it concurrently and reclaim, find which nodes can be reclaimable. This is like an example. We have some roots. The free list is defined to be a root. The nil is defined to be a root. We never reclaim those. And so all the free list is reachable from a root. And nil is always reachable, but it doesn't point to anything. And we have to find the goal of the garbage collection is to find everything that's reachable, and the things that are not reachable, here there's one, but there should be a lot in real life. All of these should be added to the free list. That's the goal of the garbage collector. There's marking, which identifies what is reachable, and there is sweep that takes what is not reachable and adds it to the free list. Okay, this is how this abstract game goes. Yeah. So I always have two fields in each object. It can point to any object in the graph or to the nil node. Here it's empty, you're saying it's not fair. You're right. Yes, it should have two pointers and they should point somewhere. I should add this to the drawing. Yes. So I have two pointers. One of them I use as for the linked list of the free list, and the other points to nil. Right. For me, what I do in this example, when I put it to the free list, one of the pointers is used for the free list pointers, and the other one I make null. I point to nil. It's not a must. I could keep the other one. It could point to like this object or something. Depending on your algorithm, you may decide to do this or that. Also in real life, so Java promises you that when you get an object, you will get it zeroed. You'll have no pointers from old life of this object. But C does not. When you allocate an object, you could get there all kinds of things that existed when this area was allocated for another object. So I don't want to guarantee anything here. But in this example, the way it looks is that one of the pointers is used for the linked list and the other is null. Yes, when we move something to the free list, we add it to the linked list and we nullify the other. We let the other point to nil. Yeah. So the program only works on reachable nodes, but it may happen, if I change this pointer, this becomes unreachable. The program can make nodes unreachable. This is the goal of the garbage collector, to find them and add them to the free list so they can be reallocated. Once a node becomes unreachable, the program will not be able to use it anymore. And so it makes sense, this is the goal, to take it and add it to the free list so we can reuse this space for other activities. The program cannot access an unreachable node, and therefore it cannot change a pointer in an unreachable node. So anytime you change a pointer, you redirect an edge, it's from a reachable node to a reachable node. Yeah. Yeah. Exactly. The program cannot access this. The garbage collector has to spot this, identify this, and add it to here so it can be reused for allocation for other purposes. Yeah. Okay. So the goals. So we want to find the unreachable nodes concurrently with the program. So the program should be able to execute while the garbage collector is identifying these unreachable nodes and adding them to the free list. And we want fine-grained synchronization. So What we don't want is to take locks or to use compare and swap or all kinds of synchronization that usually means that things take longer, and if we take locks, the user may see pauses. So in this algorithm, there will only be reads and writes, not even a compare and swap, and definitely not a lock. So very fine-grained synchronization. The overhead should be low. We don't want to spend too much time helping the concurrent garbage collection. The program should just run without interference, at least with a low penalty on their performance. In terms of correctness, we never want to reclaim reachable objects. This is very important. This is the correctness issue. We do not want to reclaim a reachable object because then it may be reallocated and the program will use the same space for two different activities. This will be terrible. So this is the correctness. And the question whether we should find all the unreachable nodes or we allowed to sometimes not find some unreachable nodes, this is not correctness, but this is progress. We want to eventually be able to reclaim all the available space. And it is allowed to have some floating garbage, it's called. This is a term that they set, and it's used until today. Floating garbage means some things may have become unreachable while we're working concurrently on finding them, and we will not identify them. And what we usually want to say, and they guarantee, is that if something is becoming unreachable at some point, in the next garbage collection, it is for sure, it is guaranteed that we'll reclaim it. So maybe we'll not reclaim it immediately in the upcoming collection, but in the next garbage collection, we are guaranteed to reclaim it. So there will be some floating garbage, but not for too long. Okay. Terminology that you have to recall. So mutator, there is this graph that is changing while we're trying to identify what is reachable. We're doing a DFS, BFS, whatever we do, while the graph is changing. And the program is changing it. The collector is not changing it. So the program is called mutator. It is changing the graph. It's mutating the edges of the graph while the collector tries to understand what is reachable. So the program is called mutator. They started this terminology and it's used also today with advanced collectors. The program is the mutator, changes the graph. The collector is, of course, the garbage collector. So we have one thread for the mutator, one thread for the collector. This is the way this algorithm works. And interestingly, this collector will not work if you have two program threads. So it's not usable today. It's just the first attempt. And it's interesting enough. And we'll see that other more advanced collectors build on these ideas. Okay, they call shade. They have this notion. It means that I'm looking at the color of a node, and if it's white, I make it gray. If it's gray or black, I do not do anything with it, but if it's white, I make it gray. It means that I notice this node. It was white, I didn't notice it yet, but I notice it now, I shade it. I make it gray if it's white. Otherwise, I don't change the color. Floating garbage, we just spoken. This is, I couldn't identify that something is unreachable. I will find it next time. Currently, it's floating garbage. And okay, so with Dijkstra's collector, I have only one mutator, one program thread is allowed, and we use mark and sweep collector. Okay, so here is the basic collector. I have a mark phase, so I mark the roots gray. This is the first thing that I do. Here it's just nodes that are called roots. Normally it will be just look at these pointers and mark those directly reachable from the roots. Now for every gray node, I look for gray nodes, I find one, I shade its successors, its children's, I shade them, so no one is white anymore, and then I mark it black. This is how I advance this trace. And when there are no more gray nodes, this is the end of the trace. Now there are only black and white, and I hope that all the reachable nodes are black. And then the sweep phase, I go for each node once. If it's white, I append it to the free list. If it's black, I color it white. This is the sweep. Okay? Everything normal. Now there has to be a cooperation by the mutator, by the program. Otherwise, there's no way you can do a DFS or a BFS while things are changing. So when changing an edge, the program shades the new target. So if I do this change, this was the old referent. This is the new referent, and this is the parent. Okay, parent. Then I shade the new. After I make the change of the pointer, this one does not exist anymore. I shade the new node. So what it means is that this one cannot be reclaimed anymore because the collector looks for these gray things and traces from them, or if it's black, it remains black, but it will not be reclaimed. So I make sure that if I point to a node, this node will not be reclaimed. Yeah.
Does that only have just an implementation detail?
So we're now in an abstract execution. There's always GC run. So think of it, I mean, you're right that later we'll have to work with idle time where the GC is not active all the time. But in Dijkstra's algorithm, there's mark sweep all the time. Yeah.
Does that mean that the old node that was pointed to, if it was black, then this would be the unlocked garbage that will stay with extra?
If this was black and it lost its last reachability edge from the roots, then yes, if it's black, I will not be able to reclaim it in this collection, but next collection, I will not gray it and it will remain white and be reclaimed. Yeah, this would be an example of a floating garbage that I cannot reclaim this time. Okay. This so things happen like before I change the edge, maybe the collector concurrently has marked stuff, enriched it and marked it black. The collector runs concurrently, does stuff. It makes things gray and then makes things black, and maybe this is already black. And this one has another reachability path, and the collector has not yet gone through it. So this is still white, and this may be black. It could be. Okay?
The question is, how do we reclaim?
This one will not reclaim this time because it's black, but the sweep will make it white. And next time it will just remain white because we'll never reach it when we trace from the roots. Okay, so it's important that the sweep takes any black thing and makes it white to prepare for the next collection. So we can reclaim stuff. Okay, so this is the basic collector algorithm. Let's look for an example. First, so suppose this is the root. This is maybe a nil, but it doesn't matter. This is another root. We start by graying them. And at this point, we start the algorithm. So we take some gray node. We shade all its children. This one does not have children, so we don't need to shade anything, and we just make it black. And then we take another gray node, anything that's gray we can take. Here there's only one. We shade its two children, and then we make it black. And now we choose any gray node. We shade its, I think it has only one child. It has one child that's already gray. So shading a gray does not do anything to the color of that node. But shading this one will make it gray. And then we can make this black. If we take this is a gray thing, we have to shade this. We have to shade this too, but it doesn't change anything. So we have to make this gray. Now, if we take this It has no children, so we can just, so it has children, but they're gray or black, so we don't need to do anything. We can make it black. This one also has only one black child, so it can become black, and we're done. So we've marked all the reachable objects, they became black. All the unreachable objects are white, and we can sweep the white objects and add them to the free list. Okay, cool. So termination is by monotonicity. So if a node, all nodes start white, and nodes can only become darker. So white becomes gray and gray becomes black. No one takes black nodes and make it gray. No one takes a gray nodes and make it white. I'm talking during the marking, during the tracing. In sweep, we do make it all white again, but during the marking, everything starts white and it just becomes darker. The program cooperation does shade, which only turns white to gray. That's the only modification that the program could do. The collector turns white to gray and turns gray to black. So everything goes one way. Eventually, all nodes are either black or remain white, and we're done. So the correctness invariant says that there's no black to white edge during the marking. So why is this enough? So we know the roots have to be black. So the roots were marked gray, and there are no gray nodes anymore. So they have to be black. Nothing goes from gray to white during the tracing. So they have to be all black. Now, because there is no black to white node and there are no gray objects, so if I start from a root and I go to any reachable node by a path, I go from black to black to black to black. I cannot go to gray because there's no gray nodes, and I cannot go to white because there's no black to white edge. So if I have this invariant, at the end, all the reachable nodes are black and whites cannot be reachable. So I'm in a good shape. This would be nice. The problem is that we assume that the pointer modifications are atomic. Everything is atomic. So like I change this edge and mark this gray like in an instant, which is not correct. I actually do it in two different actions. I change the node and then I shade it. I could do it in a different way. I could first shade and then change, but it's two operations. It's not atomic. It doesn't happen together as a one thing. So if I look at it more seriously in a more refined way to see what's actually happening, then there are problems. So we could take a lock. So we could say, I'm now changing an edge and shading its a question?
I was just asking if we said that the garbage collector is only one thread, then why would this be a problem? Because it would just be doing actions one after the other.
Right. For the collector or the mutator, between the mutator and itself, there's no problem. But while the mutator is working, the collector does stuff. And we'll have to show that this cooperation is not harmed by. And in any case, we will want to. We've kind of claimed correctness by saying there's no black to white edge. And this will not be true if we break it. If we do this change and shade atomically without looking in the middle, this will be correct. But suppose we change it and then shade it, it is possible that after changing it and before shading it, I will not have this invariant. Yeah, this invariant will not be correct between these two actions, between these two steps. Okay, so we do not want to use a critical section like a lock that will make things atomic because it's too expensive. So we'll need to do it more wisely. We'll have to do a better analysis to see that things are actually happening correctly. So we have two options. We first change the pointer and then shade the target, or we first shade the target and then change the pointer. Okay? And just to be sure that the English is not a barrier, if I have an edge, I call this the source of an edge, and this is the target of the edge. Okay? So I could first change and then shade the target, or I could first shade the target and then do the change. I have to decide what I do first. So the problem is if I do the change first and then I shade, it violates the invariant because I could change it and then there might be a black to white edge until I shade the target. After I shade the target, everything is okay because it cannot be white, it can be gray or black. But before I manage to shade it, I violate the invariant. Invariant must hold all the time. It cannot hold sometimes. It must hold all the time. So if I do shade and then change, then there is another problem, which is not as easy to see. So if I first shade this and then I change, it seems like there will be no black to white because this cannot be white, right? But here there's a problem if I move between garbage collections. So suppose I have this shade and change. This is the mutator, and it works slowly. So suppose it takes time between the shade and change. And things can happen slowly in the real world. We do not assume uh, anything about the speed between the two cores. And in real world, the core could get hot and just stop for a while to get cooler and stuff. Things can happen. We do not control the pace of these cores, and this could be slower. But here I want it to be slow. I shade, and then I wait for a while, and then I change. Okay, this is a single write. I change a pointer, and between shading and changing, things happen in the other core. Here, the collector works. So I shade it before I change. I haven't changed it yet. Now the collector does the marking, so it goes through that, colors it black, and all its children, all its descendants are marked black. Everything is good. It goes through sweep, and it makes it white. Okay? That's perfectly fine. That's how it should work. Now, after the sweep, I start a new marking phase, and I go and I do all my tracing. And at some point, I get to a situation where this is black, this may be black or gray, and now I'm going to change the pointer here because the program has no knowledge on what's happening in the collector. The collector is independent and concurrent. The program now does this change. It doesn't know that there's a problem with it. It just does the change at this time. And now the problem is that the defense we had, the shading that we wanted to do in order to prevent a black to white edge was erased by the sweep. Right? Because we moved to a new garbage collection, the shading that we did before the write, by the way, I see that you're taking pictures. It's because it's not in the presentation. Okay, so there may be another slide also that I added 5 minutes before the talk today. If you remind me, I will upload the new one. Just send me an email in case I forget. So the problem is that I do the shade before the change, but the previous sweep erases this shade. I'm not going to shade anymore. I'm just going to do the shade. I'm just going to do the change. And the change without shading is very, very problematic because I can create a black to white edge. So this is more involved to see how it happens, but it's also I don't have the invariant. And here it's seriously flawed because here I will really reclaim this node. There's no way I will see it because if it's black to white here and the collector will now go on working, it will just reclaim the white node if there's no other way to get to it. So whether if I choose change and then shade, I have an interval where the invariant is not correct. If I do shade and then change, I'm completely doomed because the shade can be erased and then the change will come alone with no protection against black to white. Okay? Or should I repeat this? Yeah.
זה קורה בתהליך של העמק, או שזה רק כשאנחנו רוצים להחליף איזה קשר?
So the program just shades and change. Okay, this is the part of the program. Here it is in the time line. It shades and then it changes the edge.
שהיא רוצה להחליף מצביע, לא קשור למה שמתמודד אמרת שהפרויקט.
The collector will happen concurrently. Okay, the program just does this. It wants to change an edge, it shades, and then it changes. The problem is that the collector runs a sweep, which just erases this. And then during the next mark, the change takes place without any shading, and then it's doomed. Okay? Okay, so what are we going to do? So we're going to do change and shade. Okay, if we do that, we don't have no black to white edge invariant, but we'll use a better analysis, a more refined analysis. The invariant is not preserved, but we'll have a finer invariant. Actually, we'll have two invariants, a more detailed invariant that will work throughout the execution. So these are the two invariants that we want. Let's start with P2 because it's similar to what we had. We'll say there is only one black to white edge in the graph. Only one. We allow one, but only one. And it's the one that most recently written by the mutator. So if the mutator does change and shade, it's allowed for this to be for this interval it was just changed and not yet shaded, it's allowed to be a black to white edge. No other edge in the graph is allowed to be black to white, just this one. So we allow this. But with this, we will not be able, what?
No, I was thinking it was a problem, so now I make the problem valid and then
No, this is not good. I mean, if we only had this, we could not prove that the garbage collection works. And so we add something. But you're right, we're just saying we allow that, which is a problem, but we add something that will be good enough for us, and we will be able to prove that both are maintained all the time. So the other thing we say is for any white reachable object, let's have a picture. So for any white reachable object, I have a propagation path. What is a propagation path? So it is a path, hopefully reachable, but it doesn't matter. And we say there is a gray node in the beginning, and then only white. Then only white nodes until this white reachable node. So for each white reachable node, there is a propagation path that starts with the gray node, continues in white nodes, and reaches it. Why is this good? Why is it good for me to have a propagation path? It's because the collector will find this, because the collector takes a gray node, it makes all its children gray, and then blackens this, but then the gray will come here. And when this is handled, the gray will come here, and eventually this will become gray and black. So if there is a propagation path all the time, then it's guaranteed that eventually, we'll prove it formally, but we feel intuitively that this will eventually let us notice this node. So we're going to have a propagation path for each white reachable node, and this black to white only one edge, which is the last writing of the mutator. And with both of them, we'll be able to go on and see that they always hold, and then that the collection is correct. Yeah.
But for that one edge, P1 does not hold, right? So necessarily, or exactly does
No, if there's a black, this doesn't worry about black nodes, right? This is just saying if you have a white reachable node, which is our greatest fear, then so I see what you're thinking. You're saying this is black. It now points to this white because there was a change. We haven't graded it yet. But what it will mean, and if you think of it, it must be this white was reachable before I did the change, right? I'm doing the change. Before I did the change, this white was reachable. So there was some propagation path. There is an example here, so let's look at it. So, for example, suppose the last edge that we wrote is a black to white. There has to be, this is a reachable white. There has to be a propagation path somewhere else that reaches this white. This is what we're guaranteed by this combination of two invariants. And this is also true because this was reachable before I wrote this edge. And if it was reachable, it had some propagation path before that. And so this is the way it's going to work. So let's take a 10 minutes break and then do this. Okay. So let's do two observations, really simple observation. Throughout the execution, I want to say, first of all, if there are no black to white edges, and I'm talking after marking the roots and until finishing the trace. Okay, this is the time that interests me. I want to make sure the invariants hold. So if there are no black to white edges throughout the heap, then then the two invariants hold. Okay, let's see why this is true. The first one is basically trivial. If I allow only one black to white edge and there's nothing, then fine. I can allow it, but no one uses my allowance. Sure. Then the P2 holds. P1, I have to show that if there is no black to white edge, then there is a propagation path to any reachable white node. So how do I prove it? So suppose this is a white node that is reachable. And so let's look at the root that and the path. So suppose let's do another. So this is the root, and this node is reachable from the root, and it's white. Okay. Now I want to claim that there is a propagation path into this node. So what do? I go back. Now I start going back, and so there's no black to white edge. So this could be either white or gray. If it's gray, then I'm done because I have a propagation path. If it's white, then I can continue, and I know the root has to be either gray or black. So if it's black, then this has to be gray or black. And so when I go back, at some point I meet something that is not white. Because this is gray or black, the first time I have to meet something that is not white. At that first time, it cannot be black because there's no black to white edge in the graph. So this has to be the first time that I see something that is not white, it has to be gray. And I have a propagation path now because gray, white, 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 white is the propagation path. Okay? So this is stated here. But if there's no black to white edge, my two invariants hold immediately. Okay, so we will see cases where we get that and we don't want to claim it again and again. This is the way to show it. So, okay. So the second lemma says that if I shade any node in the graph, and before that the invariants held, then they do hold afterwards. Why is that true? So first of all, if there is a black to white edge, maybe I made the white gray and then there's no black to white edge. Or maybe I grade something else and there's still the same black to white edge. So P2 just is kept trivially when I gray something. Now P1, maybe there was this propagation path and now I grade this. So in my propagation path, something was shaded from white to gray, but that doesn't kill the propagation path, it just makes it shorter. So if I gray if I shade anything outside this propagation path, it doesn't matter. And if I shade anything in the middle of it, it just makes the propagation path shorter. So, okay, it's it's the same, basically the same proof. So, these are two things. If there's no black to white edge, then I'm okay. And if the invariants held and then I shaded something, they still hold. Okay, and this is another slide that you don't have, and if you remind me, I'll upload it. Okay, so now I want to say the statement of P2, it says this black to white edge is the last that was written. It means that there's only, by its statement, there is only one mutator, because what is the last that has been written? If there are two mutators, there are two last written edges. This is just, by definition, it relies on only having one mutator. And this is fine because the algorithm assumes that, and it will not be correct if you don't have that. So you have a single mutator. And also, I want to say that P1 is enough to show that the tracing is good. So why is it enough? At the end of the marking, there are no gray nodes. This is how marking ends. So if there are no gray nodes, there couldn't be any reachable white node. Why not? Because if there is a reachable white node, then there is a propagation path, and then there is a gray node. But if there's no gray node, there couldn't be a reachable white node. If there's no reachable white node, it means that all reachable nodes are black. There are no gray nodes, just black and white. And white nodes cannot be reachable because it would imply gray. So if I have P1, I'm done with the proof. I know that any reachable node is black. And now I can go to sweep. So this is great. So, but in order, I couldn't take P1 and just claim inductively that it holds all the time. I will need P2 in order to show that both of them are maintained all the time. That's why I need P2, just to show that P1 is preserved. Is this clear why P1 suffices for the proof? Okay. If not, then in your homework, you will probably show this. It's like 5 sentences or something. Okay. So, what I want to show is that both invariants hold throughout the execution. Okay, so after root scanning, both of them hold because there are no black to white edges. So what do I do in the beginning? I take all the roots and mark them gray. There's no black in the graph. If there's no black, there's no black to white edge. And we've said if there's no black to white edge, the two invariants hold. That was our first lemma. Great. So after the root scanning, after marking the roots, everything, shading the roots, everything is okay. I have the two invariants. Now I have to show that whatever is done on that graph, any step that the collector or the mutator are executing, I keep the two invariants inductively. So this is the base. And now I'm going to do induction on the number of steps. And we show that each step preserves both of them. So I assume both of them hold before the step, and they will hold after the step. Okay, I want to say that we assume that no two steps happen concurrently. And I want to explain why, but I will assume there is a single step happening. Either the collector or the mutator is doing something. So in general, in concurrent computing, we always assume that nothing really happens concurrently. And this is fine theoretically, but let's explain it practically. If you're writing a value to some cell in the memory, you're writing it to the cache. And so when a core writes it to the cache, there is like a full protocol called MESI. If you studied the hardware courses here, there is a MESI protocol that makes sure that if you want to write to a cache line, no one else holds that cache line. So you're alone touching that cache line. So if you're writing, no one reads and no one writes that cell in the memory. You're the only one who has the cache line. So you write to it and you're alone. Nothing can happen concurrently to that cache line. So if two cores want to read the same cache line, that's fine. It is shared between them. And then they can read, but then it doesn't matter. Maybe practically they read it at the same time, but it doesn't matter. I can order them as I like. It will not change the semantics of the program. If this guy reads 3 from X and this guy reads 3 from X, I can say that one of them happened before the other. There's no there's nothing that will change if this happens first or this happened first. So in practice, and of course, if someone writes X and someone reads Y at the same time, I can choose any order that I like. It will not change the semantics of the program. Nothing will change if one of them happens first. So I can say that each step of each of these cores happens alone without anything concurrent to it. And now I'm thinking of the entire execution as this core executes a step, this core executes a step, and then I'm only doing the induction on a single step of either the mutator or the collector. So, okay. So this is what is said here. So what does the mutator do? It just chooses an edge, it changes it and shades it. Chooses another edge, changes it and shades it. This is all it does. Remember, we're in a graph abstraction thing. There's no allocation, no integers, nothing. There's just, you change an edge and you shade it, shade the target. Change another edge, shade the target. So the shade does not kill the invariant. We've seen that in a separate lemma. If anyone shades anything and the invariants held before that, shading did not foil anything. So the invariants still hold. So the only problem is the question is, if we had the invariants before changing, do they also hold after the changing? So this is what we have to show. Okay. So now we change an edge and we want to show that it preserves the invariant. So one thing I want to say, after I shade, there is no black to white edge, because after I change, there could be one black to white edge, and this specific is the one that I changed. Could be nothing else. If I shade the target, then there's no black to white edge anymore, because I just shaded the only target of a possibly black to white edge. Okay, so the mutator changes, so I have to show that it preserves P2 and P1. So P2 is the one that says there's only a single black to white edge. So before the change, there were no black to white edges because I finished the previous write and then I finished the shading of the previous modification and therefore there were no black to white edges. And now, if there were no black to white edges, after the change, only EI may be a black to white edge, the one that was changed. And that's perfectly fine with P2 because it's the recently modified edge and that could be black to white. That's fine. So we preserve P2 when we do a change. And now we have to show that the change preserves P1. So before P1, each accessible white node, reachable white node, had a propagation path. There was a gray, white, white, white path that reached it. So we have to show that this is not foiled by the change. So we look at two cases. If the source of the modified edge is black or white. So we're changing an edge and we're asking what the parent is. Is it black or is it white? Black or white or gray, okay? Black or different than black, or not black. Okay, so if it's black, then the lost edge was not. So what happens when I change an edge? I lose all the propagation paths are as they were before, except paths that went through the edge that was lost. One edge was lost in the graph because I did this change, and maybe I lost some propagation path. But if this is a black node, then no propagation path goes through this edge, right? Propagation paths only have gray and white nodes. So I did not destroy any propagation path before the change. Any reachable white node had a propagation path. It should have also after. I did not interfere with any propagation path. So if the parent was black, then I'm fine. Now, if the parent is not black, it's white or gray, then great. After the change, there are no black to white edges because this guy is not black. And I'm only allowed to have black to white edge as my last modification, my last edge change. So there are no black to white edges. And we've shown that if that happens, we have both invariants holding. So we're done with both options, and we know that when the mutator changes an edge, it doesn't foil the invariants remain correct. Say that again, or you you don't look unhappy? I thought you look okay. So I'm saying if at the point where I shade, I do not kill the invariants. And now I've shown in these two possibilities, black or not black, that the change does not kill the invariant. So both shade and change do not kill the invariants. The invariants hold also after any step of the mutator. Mutator does not make the invariants incorrect. So, but there is something here that may be unsatisfying that I'm saying here. I'm just going to this black box. I've changed this, and maybe, so this was maybe gray, and maybe this was a propagation path for someone, and I killed it, I eliminated it. So maybe someone lost the propagation path in the second option. And I just went to some black box lemma saying, there's no problem here. So let's talk about this. What happens if this is gray and this is white, and I move this edge and this doesn't have a propagation path anymore? Yeah.
It becomes unreachable.
Right. That's what happens here. It's possible to make some node unreachable, and it's okay. If this became unreachable, it will be a white unreachable node, and it doesn't have to have a propagation path. So it's okay. It's not something that we did wrong. In any case, both shade and change by the mutator do not make the invariants incorrect. They maintain the invariants. Okay. This just says what we said now. Okay. So now we want to show that the collector preserves the invariants. So if we look at it from a coarse grain, what I do, I go for the roots and I shade them. That surely makes no problem. And then if I find a gray node, I shade the children and make them black. If all of it happens together atomically, there is no problem, right? So the collector may shade a single root, it may check the color of a node, and then it may shade the successors of a node and make it black. Any of these will not make any problem. But, this is not atomic. This means that some steps are taken, and we have to check in the middle that nothing is ruined. So if we look at it atomically, there's no problem because I make all the children gray, and then I make the parent black. So surely I don't create any black to white edge. And also I don't destroy any propagation path, because if I had a propagation path from the parent, I mean, I have this parent, and I'm graying all its children, and then I'm making the parent black. Any propagation path that goes through these things, and when I make this black, it cannot be destroyed because, I can start from the child, the propagation path. Anything that goes down, can start a gray node from here. So in any case, I'm not doing anything bad, but it's not atomic. It's not like I'm graying all of this and blacking this in a single, atomic step. There are several steps that's happening. And what's happening is that I'm going for each child of this node, I'm going to shade it, and then I'm going to make the parent black. And in between, the mutator may change edges, shade change, do whatever he wants. And we have to make sure that nothing bad happens. Okay? Yeah. No, it's not atomic. Anything had. So this is atomic and this is atomic, but all of this is not atomic. Exactly. So the collector does not change pointers, but while it is working on this node, the mutator may change pointers for this node, and we have to make sure that nothing bad happens. Yeah. Cool. Okay. So we know that this and this will not create a problem, right? Here I'm just reading, okay, I read a new old value, but this will not create a problem. I'm not changing anything. This is shading, and like we said in the second lemma, in our observation, shading never eliminates or makes the invariance incorrect. So I'm okay here, but now I make something black, and of course, if I know that all my children are gray, then I'm fine. I'm not losing any propagation path. I'm not creating a black to white thing, but I don't know that children will not change while I was working. So I really have to look at this and see that nothing bad happens when I'm making it black. Yeah. Right, that will be the claim. We have to worry also about propagation paths, but we'll have to make sure it's okay. But yes, this will work. Yeah. Okay. Okay. So let's look when I'm making this black. So if all the children are gray, then I'm fine. Why am I fine? Because blackened node is not on a propagation path. All the children are gray, so propagation paths begin below it. And also, if I'm not creating a black to white edge, so I'm not interfering with anything. I'm just black to gray edges are made, but it's not. No one cares about them. So, so if not all, so how can anything be not gray? So I've made all my children gray, and if no one did anything, then it's fine. So how can it not be gray? Maybe someone changed an edge here, and maybe this is white, right? But this, if the mutator did this and then went on and shade this, then this would be gray, and I'm fine. But it could do this and then do this. Maybe this was white, and maybe it's in the middle of this, and it didn't manage to finish and shade the modified edge. So my only worry is that the mutator is in the middle of modifying an edge on the parent, right? That I'm going to make black. It changed an edge and it didn't come to shading it. This is what might worry me. So first of all, black to white edge is created, but it's fine. Like you said, it's maintaining P2. It's the most recent modified edge. That's fine. Now I have to make sure that I'm not killing any propagation path. I'm not eliminating something that existed before I made it black. So how can I lose a propagation path? This was gray, and maybe this thing that I added here was white, and it had a propagation path before I made it gray, and also before this modification, right? If it had a propagation path before this modification, I think I have thing like that. So this was changed by the mutator, and this thing must have had a propagation path before the modification. Why? Because before the modification, it was not accessible from here, right? So this was gray before I made it black, and you could think of it as a new propagation path. But this one, before the modification of the edge, had a propagation path because it was reachable, and there was this edge did not exist before I changed this one. So it had to be accessible from a different propagation path. And this one still exists for this white object. Okay? Should I say it again? No? I mean, no or yes? No need. Okay, cool.
If it was gray, then it would possibly a root. Because
If this was gray,
no, you're saying there's an edge from the black to the gray, and then you changed the gray to white, and you added the edge from the black to the white, right?
I moved this edge to here.
So before it was, because it was gray before,
Which one was gray? This one? This one? Okay, that was a long time ago. That's history, right? I made all my children gray. But yes.
you added a new white one, or you made the gray one, you made the gray one white, and you added
No,
a
no,
new
no. The gray one, I never take a gray one and make it white. They always become darker. I just change it, and now maybe there is a white child.
okay, you didn't make the gray white, that's what I didn't.
No, no. This is a change of an edge. It's not like a change of this node. A change of an edge. This is a new node that became a child. But I'm saying, it was white, so it had to be reachable before the modification, and it had to have a propagation path. And this still exists, so I'm not worried about propagation path for this node.
And because that node is gray, you also know it's reachable because gray is a root.
Gray, I don't care about. It's not part of my invariants because gray is good. Gray is going to be traced. I don't worry about. It's not a concern. It doesn't appear in the invariant, so I don't have to prove anything about it. Yeah. Okay. So what? So if this was unreachable, no. So you cannot. The mutator, the program is not allowed to touch any unreachable node. It cannot access them. So it could not point to it with this edge. So, more questions? Okay, so we basically have the proof. We know that both the steps of the mutator and the steps of the collector do not foil the correctness of the invariants. The invariants remain correct throughout the execution. And we know that P1, since any white reachable node must have a propagation path, there has to be a gray node in the graph if there is a white reachable node. If there's no gray nodes anymore, there's no white reachable node. And so I'm fine. All nodes that are reachable have to be black. Okay, so this is the proof. The intuition, it says, if I'm creating a black to white pointer, which is a problem, then the new white child must be reachable from somewhere else. Must be reachable, this existence of a propagation path before I do the change, this is the thing that will save it. So the propagation path will make the collector find it eventually. So this is the intuition, and it heavily relies on the fact that there is only one black to white edge. Okay, so can you tell me if it will work with multi-threading, and if not, why? Even intuitively, what's the problem? Yeah.
But if there are two mutated threads, could happen that there are two black to white edges, and then
Okay.
everything falls apart because
I agree the proof doesn't work, but what about the algorithm? Maybe the algorithm still works. So what will go wrong with the intuition? Yeah, right? Exactly. So what happens? I'm making a black to white edge, and I'm counting on having another way to reach this node. But now the second mutator can kill this, and if it kills this, then this goes wrong. So let's see a specific example. Um, okay, here it is. So I'm going to make a change to create a black to white edge. So here it is. This is the red mutator, and the red mutator is now doesn't get any more CPU time, so it cannot make this gray. And next, but I know that I have a propagation path to this guy, so I'm safe because it goes out of the CPU. Other things happen. It's just not executing. And it will. If I let him do one more step, it will make it gray, but I don't. But I still have, if the collector was let loose now and had to finish the tracing, it will find this, it will make this gray, everything will be good. But now I let the second mutator, the green mutator, do a modification that kills this saving path. There's this way to get to this white node. So the second mutator does this, and I mean, it's fine even if I let it finish and gray this thing. It doesn't matter. What I worry is about this, that lost its, propagation path, and this red mutator is not given CPU time in order to gray this one. So now the collector comes, it will make this black and this gray, it will make this black, and it will go to sweep because there's no more gray objects in the graph, and it will reclaim this, which is terrible. You cannot reclaim a reachable object. If you claim a reachable object, you make the program go wrong. Yeah. So if you now have the collector, this is not an edge. This edge was changed, right? So from the collector point of view, this has two children, and it does notice them and makes them gray, but it has no way to. The only way to see this is if you look at this edge, or the mutator comes to life and makes this gray. So if you have, we assume that things are not, so you don't control the pace of the cores, right? Some cores may be slow and some cores may be fast. So there is the red mutator, it does the change, and then it is delayed. Maybe, I don't know, its core is hot or it's responding to a keyboard interrupt or something. It just doesn't get to the shade. Doesn't get to, it will get to it after the collector will finish collecting. Yeah, the collector now and there is the green guy which kills, eliminates the saving path, the propagation path, and then the collector comes and finishes mark and does a sweep, and then everything goes wrong. More questions? Yeah.
אפשר שאלה לגבי מה שראינו מקודם
The proof? You want me to go back?
בשקפים שלה, שהפכנו אותה מאפור לשחור.
Okay.
אנחנו הופכים את הצומת העליון מאפור לשחור.
Yeah, this one goes from gray to black.
אתה יכול להסביר למה לא יכול להיות במקום כאילו עוד קשת כאילו משחור ללבן שהיה מקודם?
All my children are gray, right? Now, if I let the mutator work, what it does is it change it maybe to white, but if I let it work a bit longer, it will make it gray. And again, all my children are gray. So all my children are gray except for one child that maybe because the mutator is right in the middle of an action. It just did the first step of changing the edge, but not yet the shading of the target. So there could be only one white child, and this will be because the mutator is in the middle of the action. All the others must be gray.
אז כאילו הפעולה הבאה של שניהם, לא משנה מי מהם יעשה אותה, יהיה להפוך אותו לאפור.
If the mutator comes to life, it will make this gray. The collector is not going to make this gray. It's going, maybe when it looks at this gray, it will make this gray. If you give it enough time, it will make this gray. The collector, if you let him run until the end, this will be noticed and become black eventually.
זה לא יכול להיות שתיווצר עוד מהקולקטור עוד קשת שתהפוך...
Collector does not change edges. No edge will change by the collector. You're sure that this is the only modification that's happening in the graph. If you had another mutator, that will be bad because it will change edges and then you don't have this safe environment to work with. Okay. Any other questions? Proof? Why it doesn't work with multi-threading? Okay, cool. So we didn't go through sweep, but it doesn't really pose a serious challenge. Sweep just, in this graph model, it just colors all the black objects white. For the next collection, moves only. Actually, we did talk about sweep for a while. It has minimal interaction with the collector. We'll talk a bit more about this in our next collector, but let's leave it now as is. These were the challenges that were handled. Properties. It's concurrent with no synchronization. We don't need a compare and swap. We don't need a lock. We don't need anything that's synchronizing. Just reads and writes. That's all we do. And the algorithm is theoretical. So first of all, no one would imagine marking the free list. This is a waste of time. You don't want a write barrier on the roots. We'll talk a lot about this when we do concurrent. This will be one of the challenges. We don't want to see if roots are changing because that takes a lot of the time of the program. It's unable to do with multi-threading, which is really a killer. This is not something that could be used today because many programs are multi-threading. But the ideas were innovative. It's the first one that was done. There was another concurrent one by Guy Steels, who later was one of the inventors of Java. And there was this Baker algorithm from 77, which is, well, it was not concurrent, but it was around the same time. So there were these three French guys who solved some of these issues. And then there was a paper, this was 94, and 2000, it was made part of a production JVM, this DLG collector. So this is what we want to talk about a bit next. So Dijkstra, in the paper, writes, looks at this. Our exercise has not only been very instructive, but at times even humiliating, as we have fallen into nearly every logical trap possible. That's what he says. He just went the wrong ways many times. And it has been surprisingly hard to find a published solution and its justification. It was only too easy to design what looked, sometimes even for weeks and many people, like perfectly valid solution until the effort to prove it correct revealed a bug, sometimes a deep bug. So he was surprised. I mean, these people were surprised, and these people were quite smart. And they were surprised at how difficult it was for them to design it and get a good solution because they went into some direction and they thought it was okay. And sometimes for weeks between these 5 people who were working on it, it looked excellent and you just wanted to prove it. And then they found out that there was a bug, sometimes deep, that they didn't see. And we don't see it when we look at the final solution, but it is, we're going to look at it a bit with the next algorithm. We'll see what traps you might fall into. And okay, so the next thing is the DLG algorithm. So it is, Okay, I'm sure I'm not saying the French names correctly. Maybe it's Doligez-Leroy-Gonthier. Maybe I'll call them Doligez-Leroy and Gonthier, as the Americans call them. And if you know French, you will know how to translate it to the right way to say it. So there was a paper in 93 giving an algorithm to do this properly, to fix Dijkstra. It was generational. It was for ML, which is the programming language. And then a year later, there was a paper that came out and said, oh, that paper was wrong. Now we have the right solution. And they indeed had the right solution, and they also proved it correct in a logical manner with computerized proof. Later in 2000, people in IBM did generational garbage collector for Java that was based on this collector. And so it became a production. So the original paper has some things that are very specific for ML. For example, they have some lots of immutable objects, like objects that don't change throughout the execution, and they make use of this. We will not care about this. We will talk about Java-style programming. So also they made local heaps for the immutable objects. They did all kinds of things that are very specific for ML that we don't care about and we will omit for this discussion. So no local heap, no semi-generation, no use of immutable objects, and we will not do the full algorithm and proof completely because it's too complicated. We'll have another algorithm that we'll describe until the end, but I want you to understand the main ideas and a bit of the traps that you may fall into. So we want to eliminate the free list traversal. We want to fix a race between allocation and sweep. We want to avoid repeated. So the way the Dijkstra said we should do it is just go through the heap and look for gray objects. And so for each gray object, I might go through the entire heap. This is not the way you want to do things in production garbage collector. And we want to move from change and shade that made it only possible to use one mutator. We want to move to shade and change, which is also problematic. We'll have to deal with it, but that will allow several mutators we'll be able to work with. Okay, and we'll not want write barriers on local variables on our stack and registers and global variables. For the roots, we'll not want a write barrier. Okay, so let's, because of the time and the noise, we'll just do this. And so let's get rid of the free list scan. You remember that Dijkstra said we will make a root node point to the free list and we'll just traverse it. That is redundant. We don't want to do this. And what DLG did, they added another color, a blue color. So a node could become blue if it's in the free list. And then we know we don't need to reclaim it. We don't need to traverse it. There's no need to touch it at all. Okay, so just make white, gray, and black are as usual. Blue will be in the free list, ready for allocation. And so this is the solution to traversing the free list. And since we cannot continue, we'll meet next week. See you then.